Welcome back to the same lecture 13. We have actually started this lecture 13, which I told it's a very long. In fact, I was expecting two part. I can do it, but finally it went into three parts, at least as of now. Even it may go even little longer. I don't know. So what we have seen last, you can say lecture, we were talking about why dynamics is important and what is the equation of motion, or in the sense what is motion dynamics. So what would be the two subclassification, or you can say what are the two different mapping. So one is forward dynamics, where for a given, you can say, torque vector, what would be the motion variable that we are looking, that is what forward dynamics. Whereas for a given, you can say motion, you can say motion variable and its derivative, what would be the, you can say, input vector, that is what we call inverse dynamics. So the forward dynamics is nothing but a simulating or analyzing the system, whereas the inverse dynamics is very close to controlling the manipulator. And the last slide where we stopped, we stopped like there are several methods are available. We were stopped at two major method which we are going to focus in this particular lecture. So one is Euler-Lagrange and the other one is Newton-Euler method. So this particular second part, we are going to talk about Euler-Lagrange or Lagrangian formulation method, or Lagrangian Euler, whatever way you can call. So this particular method we are going to talk. So here the very basic assumption says that this is rigid body system, and what Lagrange says that if there is a energy difference, so there is a energy difference, then there is a motion exists. The motion exists only there is a energy difference. That is what he tried to understand. It is actually very close to the energy method, where it is a conservation of energy, that basic principle, and the Euler equation was derived where with respect to momentum the same relation he was used, and he was saying that there is a energy difference, then there is a motion exists. Since the first prerequisite or assumption what we said, it is a rigid body, so then you can see that what are the energy would be there in the rigid body. So only two kind of energy we can realize. So one is actually kinetic energy, so the other one is actually potential energy. Okay, so then there is actually these two difference, that is what, so the Lagrange realized. So that is what we are hereafter going to call Lagrange. So Lagrange is actually kinetic energy minus potential energy. If this exists, the Lagrangian is non-zero, then what you will actually get, get the motion. So for example, to understand this, so you can see that this is actually a simple pendulum. So this is the equilibrium position where you can see potential energy is zero and kinetic energy also zero. Now I am actually pulling that pendulum little far. What I am trying to do, I am actually inducing some potential energy. Now even there is no kinetic energy, but there is a potential energy there. So if I leave this, what happened, this actually start oscillate, and if there is a dissipation, or you can say friction, it actually gets settled. If there is no dissipation, then it would keep continue, the motion continues, right? So similarly, you can see that the other situation where the pendulum is here, and I am actually trying to induce the velocity, in the sense I am just hitting it, that pendulum. So what happened, this will actually energize, in the sense the kinetic energy started, although the potential energy is zero, then you can see that this also start oscillate. Okay, so this is what the basic idea. So energy is a scalar, and what Lagrangian also going to be a scalar, which is nothing but difference between kinetic and potential energy. This is what we are going to use, right? So now this Lagrange is actually Lagrangian. The Lagrange used this particular scalar quantity that hereafter we are going to call Lagrangian. Once this Lagrangian is there, then what we can see, so we know what is momentum. What is momentum? So momentum is actually mv, or some people write so m into dx by dt, right? So now the time derivative of this, what will happen? So that would be force, right? So now you can actually see that this energy is what? So energy I can write, so force into displacement, right? Or you can say the other way around, you can write what you can write, it is actually you can write F into V into, you can say something called S. So in the sense time, right? So now this is what all happened. So now if I actually take partial derivative of this power with respect to V, what it will get? You will get F. And now this equation will be, if I take partial derivative with respect to V, so what I will get, that would be having F. into s, in the sense I would write t. So now I'm actually like taking the time derivative of this, what I will get. So I just try to give some, you can say, equal. So now if I do this, what I will say, this will be f t, and this is actually like nothing but f, right? So now the similar way I can write f into displacement. So this is what your energy equation. Now if I take partial derivative of this with respect to d, so what I will get f, right? So this is what very basic. Okay, now I can see that this is actually like energy component and this is actually like, you can say, power component. I see the difference, that difference supposed to be equal to what the input force. This is what kind of realization. So based on that, you can see you got the generalized equation, what you call Lagrangian Euler equation, where dou L by dou Q dot will give actually like something like you call momentum. Then you take time derivative of that, that is equivalent to what you call something like a force, and then you are taking a time derivative of, you can say, dou L by dou Q. So that would be equivalent to 0 if it is energy equation, but right now we are talking about Lagrange, so that would be equivalent to the external force, which we are simply going to call as a input force. That is what we are actually like trying to say. So now in that sense, what would be the general expression for kinetic energy? So kinetic energy is actually like generally what we write in a scalar quantity, and the scalar variable, in the sense only one dimensional variable, we write half into mv squared. So in the sense half into m, you can say dx squared, dx by dt whole squared. So this is what you say as kinetic energy. But now this is no longer actually like a scalar, and scalar in the sense the variable is no longer as one dimensional, it is having a vector of variable. Then you can see that this m also like would be consist of several. So you can see like what we can write. So we can write v squared as a vector form, that is v transpose into v, right? So now there is a inertia matrix involved, so v transpose into m into v. So this is what your kinetic energy. And the potential energy also we can write as mgh. That is also I am going to write in a general form, because the h is actually like vertical component along the gravity direction. So that I can write mg, you could call actually like y of that particular axis. Okay, so that is what we are actually like going to write. You can see that. So this is what you can see the kinetic energy relation. Since we are assuming that is a single mass, so then m can be a scalar and it can be taken out. And this is actually like what you call the, I think there is a typo. So this is what the case. Okay. So now you can see this bracket is not here. So I will correct it and upload it in the Moodle. But right now you can actually like see. So this is what the correct form. And you can see that this is actually like kinetic energy due to the translation mass, but this is the kinetic energy due to the rotational mass. So now this rotational mass I can write as you can say I omega squared. If it is actually like scalar quantity, now it is actually like vector omega transpose, and I is a matrix, then it is coming. So this is what you can see the rotational kinetic energy, and this is the translation kinetic energy. So the total kinetic energy is actually like a sum of this, and total kinetic energy of the system would be sum of individual. Okay, so that's what this I goes to 1 to, you can see n number of bodies. I actually like goes 1 to n number of bodies. Okay, so similarly you can go with the potential energy. The potential energy is actually like written in mgh form. That mgh form I am actually like writing in a very general form. So where g is a vector, that would be, for example, I am assuming z axis is the gravity. So this is the g vector, that would be having a gravity term in here. Okay, so now the vector is actually like a transpose to your what you call the position vector. So the position vector is x, y, z. Now you can see that automatically the z would be coming if in this case. So now I am taking, this is actually like z axis and this is the x axis, and somehow actually like this is y axis. Then you can see that this is not going to happen like this, right? So then you can see that the g will come somewhere. So that's why we are actually like writing in a general form. You can see that this is what you call the potential energy relation. Okay, so now the potential energy has done. So now we will actually like see some some analytical example to get it. So for understanding this, I am taking a 2-hour serial manipulator where I'm actually like making a very, very simple case. What that means? So I'm assuming that the mass is concentrated at the end of the link. So in the sense that there is no gravity, you can say that this is a massless. So then what you can see, there is no translational inertias are part of it, right? That is what, just for making it very simple. So now if I write kinetic energy, what would be the kinetic energy of m1 x1 dot squared plus of m1 y1 dot squared. Okay, this is the first mass. Then the second mass is actually like of m2 x2 dot squared plus m2 y2 dot squared, right? So in addition, the translational kinetic energy you have done, so you have done that. So right now the rotational kinetic energy, so here you can see that there is no rotational kinetic energy straight away, it is coming, right? Why this I, we assume that massless rod, so this would become 0. So then you can see that this is the kinetic energy which is for the total kinetic energy. And similarly the potential energy, what you can see here, it is mg, okay, y1 m1 g1 then plus m2 g y2, right? This is what we are actually like writing. So for that we are writing x1 as actually like L1 C1 and y1 is actually like L2 C, sorry, L1 S1, and x2 is actually like L1 C1 plus L2 C12, and y2 is actually like L1 S1 plus L2 CS12. If I take dot product, x1 dot would be minus L1 S1, so y1 dot would be minus plus L1 C1, right? So here actually like theta 1 dot and here also theta 1 dot, because we are taking time derivative, right? So now if I take x1 squared, then you can see that it would be L1 squared S1 squared theta 1 squared, and y1 squared is actually like L1 squared C1 squared theta 1 dot squared, right? Theta 1 dot squared in the earlier case. So that is what we are trying to do. Similarly x2 y2, and we are actually like trying to take the derivative of that. So you can see that this is what we are trying to do. So now you can see that the time derivative we have taken, and we are actually like trying to take the kinetic energy in the overall equation. So now if I take that substitutions, what we'll get, so you'll get the final simplification is like this. Now although you have not used the rotational inertia, but you can see that this is a rotary ring, so you can see that the rotational inertia is in part, right? So that is what we are actually like seeing. And similarly the potential energy we can actually like take forward, and you can actually like see, you can see the potential energy we derived in this form, right? y1 and y2 we have substituted and we got it. So now we can actually like see that this is what the final equation of the Lagrangian. You substitute kinetic energy minus potential energy, this is what the equation. So now what we are interested to find tau 1 you can write, you can see the q1 is nothing but here theta 1, so q1 dot is actually like nothing but theta 1 dot. So tau 1 here is actually like, you can see the vertical axis rotary torque, or you can say rotational torque. So this is what we are trying to find. So we can see that whatever you have L, so you take the time derivative you have done, and now you are actually taking the partial derivative with respect to theta 1 dot. So you can see that the theta 1 dot is having only here, right? So that, and here. So you can see that you are trying to do, so you are taking the time derivative of that. So I am actually like expecting you will do your own, but I am just giving the final equation here. So similarly you can see theta 1 also you take, and this is what dou L by dou theta 1, and this is dou L by dou theta 1, and this is theta 1 dot. So now this is actually like I need to take the time derivative, I am taking it. So if you take time derivative, what happened? So this is actually like theta 2 time, and this is theta 1 dot time, this is theta 2 dot time, and this is theta 2 of time. So like that there are 4, you can say, terms are there. Right? So now what you can do, you can apply the what you call the UV formula in differentiation, and then you can see that the final equation look like this. So now this is actually like d by dt of dou L by dou theta 1, and you have already this, so you can say take this, subtract with this, so that is what you call the tau 1, right? So what is tau 1? So tau 1 is d by dt of, so dou L by dou theta 1 dot minus dou L by dou theta 1. So now you have this already, and this is also you have, so you substitute, this is what you are tau 1. So similarly you can extend the second equation, so you can see this is what, so you get dou L by dou theta 2 dot and dou L by dou theta 2. So this is what we are trying to do. So this is what one, and this is what second one. Now you can actually take the time derivative of this. So it is straightforward. This is going to be double dot, and here you have two equation, or you can say two variable, then you will get that subequation. So now this is what you are dou L by dou theta dot with the time derivative, and this is what dou L by dou theta 2, and you can actually substitute, that is what your tau 2 has come. Okay, so this is the way we have actually like done with the Euler-Lagrange. So now you can see that tau 1 and tau 2 we got it, and we can rewrite that into a matrix form. That we will do it in you can say part 4. But right now you can see that what we did, so we have actually like taken the you can say kinetic energy, and we have actually like, so we have taken a kinetic energy and a potential energy of this particular system. So this particular system, and actually like we have derived individual equations based on the Euler-Lagrange. Okay, so with that I'm actually like stopping this particular lecture, and I will come back with the part 3 for you can say the what so called Newton-Euler method. You can see that Newton-Euler method is remaining. All slides are coming under Newton-Euler method. We'll see that in detail. So what we have done tau 1 and tau 2 we derived, and with that we have actually like stopped for you can say Euler-Lagrange method. The next part, or you can say next lecture, would be on you can say the second method, what you call Newton-Euler method. Okay, so that is what we are going to see. We will come back with that. Thank you.